Okay, in this lecture, we want to talk about ordinary differential equations with variable coefficients. So in the last lecture, we talked about constant coefficients, and we showed how to find a solution for those equations by forming a characteristic equation and then finding the roots of the characteristic equation, substituting back into the form e to the lambda x. In this particular case, we're going to look at differential equations that have variable coefficients. So this method's pretty useful for a lot of common functional forms, but it's not particularly useful for some other functional forms. So we're going to apply something called the power series method. And basically the limits of the power series method are that you don't want functions in your coefficients that have negative or fractional powers. So what's a power series? Well, basically a power series says that if we have some, function expanded around some point x sub 0, that we can write a series where that's a constant and then a constant times a first order term and a constant times a second order term and so on. And if we expand it around 0, which is most commonly done, then it becomes a constant times x, a constant times x squared, a constant times x cubed, and so on. And different functions are modeled with the power series by changing whatever a sub 0, a sub 1, a sub 2, and so on are. So, there are all kinds of familiar series. Here's some examples. 1 over 1 minus x can be written as a series 1 plus x squared plus x cubed and so on. The exponential function has a classic geometric series. The cosine, another classic series. The sine, another classic series. So notice in some of these, specifically the cosine and the sine, every other coefficient is equal to 0, with the cosine having even powers of x and the sine having odd powers of x. So these are just familiar series that we find in mathematics for various functions. So what are some of the limits of the series? Mostly the power series can be used as long as the series converges. So a test for convergence is the so-called radius of convergence r, and ideally we would like for r to be infinite, but it needs to at least be greater than 0. And here are a couple of expressions for the radius of convergence, a couple of formulas. M is our coefficient, or is our index of our sum. The a sub m's are our coefficient. We're going to take the limit as m goes to infinity and evaluate r, and you would like for r to be greater than 0. What this really means, is it really means that you can use a power series estimation as long as the higher order terms in your power series are approaching 0 and getting small. So I should be able to say, for example, after the kth term in the series, where k could technically be anything, but you would like it to be 5 or 6, that if I add a higher order term, the coefficient is becoming so vanishingly small that I can essentially neglect every power above some predetermined number. And vanishingly small depends on your application, but it can be anywhere from half of a tenth of a percent to a couple of percent. Just depends on what you're trying to model. So that's the limit of the power series method. Here's a general differential equation, and basically what we say is that we can use the power series. This differential equation is going to have a power series solution if p of x, q of x, and r of x can be represented by power series themselves. So in other words, if p, q, and r, if we can find a power series representation, then we can find a power series solution. So the strategy is, first of all, you assume a solution. This is what we always do in differential equations. We assume a certain solution form. So in this particular case, we're going to assume y can be written as a power series, and then we're going to look at the first derivative of y and the second derivative of y. This is a second order differential equation, and so we'll need to substitute y prime, and y double prime. So here's both the term-by-term expressions as well as the sum expressions for y and its derivatives. Okay, so after you find y and its derivatives, what you're going to do is you're going to substitute those back into the differential equation. And at the same time, you're going to substitute the power series representations of p, q, and r. So everything in the differential equation, y and its derivatives, the p, q, and r functions, we're going to substitute the power series expression. We're going to simplify everything, and then what we're going to do is gather like powers of x. And we're going to force the coefficients with like powers of x to be equal on the right-hand side and the left-hand side of the equation. So if we wanted to list in steps, basically first we find y and its derivatives as a power series, and we substitute that into the ordinary differential equation. We also find if r, p, and q are not constants, if they're functions, then we find the power series for those and substitute as well. Then what we're going to do is equate coefficients of equal powers, solve those equations simultaneously to find the coefficients. Usually what happens when you do that is you find that higher order coefficients can be related to the zero order coefficient in what's called a recursion relationship. So here's an example. The differential equation is y prime minus 2y is equal to 0. So first of all, we're going to assume this power series solution, a sub n x to the n from 0 to infinity for y. And I substitute that in for y, and then I take its derivative, and I substitute that series in for y prime. And then what you do is you play around a little bit with the index of summation. So you'll notice that in this term, we basically just move this second term over to the right-hand side and rewrite the equation. Now notice this sum runs from 1 to infinity, and this sum runs from 0 to infinity. So what I'd like to have a sum here that runs from 0 to infinity, and I can do that by basically substituting n plus 1 for n. And so then that makes my coefficient here go to n plus 1. When the old n was equal to 1, the new n will equal 0. When the old n was equal to n minus 1, the new power will equal x to the n. So by changing the indices on the sum, making a simple substitution for n, then I can get the left-hand side and the right-hand side both summing over the same range, starting at 0. And so what I can then do is I can set powers of x equal. So I can set x to the 0 on the left-hand side equal to x to the 0 on the right-hand side. And that would mean then that a sub 1 is equal to a sub 0. So let's look at that. So by equating coefficients of like terms, you basically can obtain the recursion relationship. So notice I'm basically just saying the left-hand side has x to the n and the right-hand side has x to the n. So the coefficient on the left and the coefficient on the right are going to have to be equal. So that tells me that a to the n plus 1 is 2a to the n over n plus 1. So if I choose my first coefficient to be a sub 0, then notice that each successive coefficient can be written in terms of a sub 0. So I can then come in and make a substitution in my expression, because notice here, if this is the 0th term, the first term, the second term, the third term, what I've got going here is I've got 2 to the n power over n factorial times a sub 0. So that then gets substituted here into this general expression, and that's basically that's my solution series. So here's another example, y double prime, xy prime, and y. So once again, we assume we have a series solution, and we find y and its derivatives. and then substitute that into the equation. So this bottom part of the page here is y double prime substituted here. This term will be xy prime. This term will be y. Taking the 1 series in x to the n minus 2 and putting it on one side, and taking these two terms and combining them and putting them on the other side, I get this expression. And here's that repeated so that we can kind of look at it all on the same page. Now what we're going to do is we're going to do that change of index again on the sum. So what we'd like to do is we'd like to have the left-hand side run from 0 to infinity, and the only way to really do that is to let n go to n plus 2. So if we replace this with n plus 2 here, then we'll have n plus 2 is equal to 2, and so if you subtract 2 from both sides, then that sum's going to run from 0 to infinity. N becomes n plus 2, and n minus 1 becomes n plus 1, and n minus 2 becomes n. So all of these coefficients are shifting from the index of the sum to the coefficients to the subscript to the power. They've all shifted by 2. And so then what that does is that then does a couple of things. It changes the subscript on this a, which remember is what we're trying to solve for, and it also changes the power so that now the coefficients on the left hand side and the coefficients on the right hand side once again are going to have to be equal to 0. So that gives us this equation, which if we now solve for a subscript n plus 2, we get the following recursion relationship for n greater than or equal to 0. And we can do some canceling there. So a to the n plus 2 is minus a subscript n over n plus 2. So that would be the coefficients of the series. So now if we start substituting, what we find is we have a sub 0 over 2 for a2. We have an a1 over 3 for a3. So we can kind of collect all those like terms, substitute them together into a general solution, and we notice that we have this expression. We can do some collecting of terms and write that as under a summation sign, or you can leave it like this. But if we write it as a summation sign, this is what it looks like. And so notice here that a sub 0 and a sub 1 are unknowns, but all the higher order terms have been written in terms of a sub 0 and a sub 1, with the even terms written in terms of a sub 0 and the odd terms written in terms of a sub 1. So what does that mean? That means that after we do this series solution, we still have two unknown terms for our coefficients a sub 0 and a sub 1. But that shouldn't surprise us because this is a second order differential equation. And so unless you have initial conditions, you're going to have two unknown coefficients that are essentially constants of integration. So a sub 0 and a sub 1 won't be known unless you know initial conditions, and this is an initial value problem.